Good morning, bro. One minute class starts here. हेलो एवरीवन। सर प्रोबेबिलिटी का रिवीजन कब होगा? जल्दी होगा बच्चों। किधर गए ये दो बच्चों? बोले आ रहे हैं। कमान कमान ज्वाइन फास्ट। आदित्य class right now, Kusum Girish. 1 minute or 2 minutes it will start. We are doing a class on EMI and EM waves. Okay. See, chances are 70% it to be easy. 30% they can go haywire and give it tough, but 70% it should be easy. Where are you, Kartike? Lucky? Okay, chalo. Let's start with EMI, electromagnetic induction. So EMI is a very simple and easy chapter. Okay. Hi, Karan. Everybody join, start, sir. Chalo. Now, what all you remember about EMI? In electromagnetic induction, first basic definition of EMI, very simple, very straightforward. Phenomena of generation of current. So to get above 5000 rank, how much marks I should score? Hello, Half Moon, bro. How are you? How's your health? Kusum Grish, ma'am. Okay. 5000 below. I need to know your both how much you are getting your targeting in, what do you say? What do you call it as? Second PU, and then I would be able to say it. Okay. Still sick, very worried. Don't be worried, bro. Don't be worried. Because worriedness increases the sickness. So don't be. Be happy, be chill. And whatever will happen, we'll face it. Okay. So this is not the end of life. Okay. A lot of people they have done, like physics wallahs, a lot of people they have done way better. Whichever college, whichever place you go, if you keep working hard, you'll be in a top damn good position. Okay. So this is just one fight. But yeah, be ready for the fight beforehand, not like one day before the exam. Okay. Chalo. Above 90%, then 5000 below. Safe side 120 below or 120 above is like very decent. You can get between what do you say, below 5000, safe side. And like luck wise, 100 to 120, 110 to 120. 120 above is like very good. Now define EMI. So phenomena of generation of current by what? Changing EMF or magnetic field. Okay. So generation of current or EMF by changing magnetic field. Clear? Now next, what is magnetic flux? What is magnetic flux? Karthik, where are you, bro? So define magnetic flux. Flux is number of field lines crossing through any surface normally. Total number of Oh, screen not visible. You should say no. Nobody said. I forgot only. Total number of magnetic field lines crossing through any surface normally. Okay. So basically what we are saying is, okay, so this is normal to the area. This is not area normal. So whatever the field lines are crossing normal to it, that will give me the magnetic field. That will give me the magnetic flux. Okay. Kartike now wrote screen not visible. Where is the Soham and Aditya? So what did doctor say, Half Moon? And what? How did you get a, what do you say, food poisoning kind? So we all know is it what? B dot dA. Clear? So if I want to find magnetic field, B is equal to flux by area. This is called as still not visible, magnetic flux density or magnetic induction. Magnetic flux density. See, flux by area is known as magnetic flux density or magnetic induction. Clear? Magnetic induction. Now we all know phi is also equal to B dot A. So that is equal to mod of B, mod of A into cos theta. And theta is max when it is what? Here in this case, understand one very important. See, here you'll see when normal and see normal is outward. Okay, so outward perpendicular is the normal, and magnetic field also is going like this. So the angle between them is what? 0 degree. And cos 0 is what, student? Cos 0 is what? 1. So we get maximum flux in this. Now if my magnetic field lines are going like this and my area normal is this. So now the angle between them is what? 90 degree. So cos 90 will be what? 0. So here the flux will be 0. Clear? Clear? Next, what is the unit? 1 Weber. What is the unit? 1 Weber. Now 1 Weber is what? 1 Weber formula will be what? Magnetic field 1 Tesla meter square. So if I define 1 Weber, very simple. 1 Weber is nothing but the magnetic flux over an area of 1 meter square. Clear? Held perpendicular to a uniform magnetic field of 1 Tesla. Clear? Chalo. Just definition, just told it, like you don't need it. Okay. Next, Faraday experiment, Faraday and Henry's experiment. Okay. You all know about Michael Faraday, sir? One second, student. Chalo. Now let's listen to very simple but one short story of Michael Faraday, sir. Okay. So Michael Faraday, sir, who was very poor. Okay, coming from a very background family. They were like 7 siblings and around, like, I'm not exactly sure, like 5 or 7. Okay. So they were like so poor, they used to get one big loaf of bread. Okay. Now that loaf of bread would be divided into 7 people like this. 1, 2, 3, 4, 5, 6, 7, like that. Okay. And they used to get it for this for 7 days, 1 week. Okay. One big loaf. Michael Faraday sir got for 7 weeks, 1 week, 7 days. So now this bread he used to make it into 7 parts. Okay, that this is for day 1, day 2, day 3, day 4, and now let's say If he's too hungry today and he consumed 2 of it, then tomorrow he has to stay hungry. Clear? No other option. So this was bad, so bad, lit bad condition of Michael Faraday, sir. So his brother saw that there was an opening in a book binding shop. So he, told his brother that you go and try. If you are getting a job in the book binding shop, then you'll be able to earn a bit money for the family. So he went to the book binding shop. He started binding books. So whenever earlier that time when books used to come, they used to stay for at least 15 days, 20 days, 30 days. Okay. So while doing the book binding, he started reading it. Then Henry sir, he was a very famous scientist that time, physicist. He was doing some experiment with the magnetism. He came and there was a show of him. Okay. So there he wrote some 7 or 6 laws. Our Michael Faraday sir went and he cut down 2 laws. So he understood that this person is very knowledgeable. So he hired Michael Faraday sir as an apprentice. So in the night, he used to do his own experiments, and in the morning, he used to be the apprentice, he used to work. So that hard work he did, and he got the Nobel Prize. Okay. So hard work is must to students. Okay. Sure. So let's see our EMI part. Okay. Now what we have in the EMI part is our Faraday and Henry experiments. What he did is he took a magnet, north and south, and he put a coil, and he started bringing the coil near the magnet. So what he saw, whenever the magnetic field linked with the coil is changing, EMF is induced. Whenever the magnetic field linked with the coil is changing, EMF is induced. Now he tried different things. He moved first the magnet, then this one, then he moved it away also, then he moved this one away. So he quote one term that whenever relative motion between magnet and coil happens, then what happens? We see a deflection in galvanometer. Deflection in galvanometer. Let's say here. Clear, everyone? Clear, everyone? Now this includes everything. Okay. He took like bringing it forward, backward. Okay. Making the wire just coming. So what was the reason? So let's say at this instant, 10 field lines are crossing. Okay. The moment he brought it more near like here, so what happened? The number of field lines increased. So due to the changing magnetic flux, we are getting a induced current. Clear, everyone? Yes, no, yes, no. Looks like everyone is in the sleepy mode. Anybody there? Hello. Hello, hello. Yes. Harsh is there, okay. Lucky is there, clear. Do say yes or no, kids. It looks like less people are there. I'm not able to understand whether you are there or not. Shalom. Now let's see next. So what he did is next time, instead of bringing a magnet, a coil carrying current also behaves as a magnet. A coil carrying current also behaves as a magnet. So what he did? This time, he brought a coil carrying current. A coil connected with a battery. So it has a current. Now he started bringing near, far. Same thing he did. With that also he found deflection. Clear? So he got to know wherever there is relative motion. He said whenever there is relative motion, there is deflection. Clear? Clear, everyone? So EMF is induced whenever there is relative motion. And then he gave 2 laws. Faraday sir gave 2 laws. Number 1, First law was whenever the amount of magnetic flux linked with coil changes and EMF is induced. Number 2 is said the magnitude of induced EMF is equal to the rate of change of magnetic flux. So what he said, that the induced EMF is directly proportional to rate of change of flux. Clear? But the direction is opposite. So E is equal to minus d phi b by dt, rate of change of flux. Now if somebody wants to write in other terms, can write as phi 2 minus flux final minus flux initial by T2 minus T1, this also. Clear? Clear everyone? Written. And what does negative sign says? Negative sign indicates what? Negative indicates that induced EMF always opposes induced EMF always opposes the change in flux. Clear, kids? Who all are there? Put a message in the chat section. Chalo. Clear? Can I go to the next page? Chalo. Now let's everybody understand. It was for one coil turn. What if we have a coil with n turns? Coil with n turns. What will happen? E is equal to minus n times of d phi by dt. d phi by dt. Clear? Chalo. Now, so we got the EMF. What about the current? We got the EMF. What about the current? Induced current. So, we'll say, sir, current is nothing but I is equal to what? V by R. So, here E by R, EMF by R. So, minus NR into d phi by dt. Correct. Simple. Clear? Clear? Now, we'll say, sir, you got about current. Very good, sir. Very happy. What about the charge? Sir, Q is equal to what? I is equal to Q by T. So, Q is equal to what? IT. So, I into dt, let's say for a small time. So, N by R into d phi b. Correct? Clear? Clear, students? Got it till here? Now, next came the Lenz law. Anybody knows about Lenz law? Or Lenz's law? The polarity of, means the direction of induced EMF, whether it will be positive or minus, is such that it tends to produce current which opposes the change in magnetic flux that produced it. Clear? Clear everyone? Clear everyone? Now let me explain with an example. See what we are trying to say. Okay. Let's say two coils are here like that. Okay. and you are bringing a magnet. You are bringing a magnet. So this magnet here, south, here north. So when it is coming in, when it is coming inside, what you'll do, you'll produce a current so that it shows what? It shows a north here and south here, correct? The magnetic field should come like that. So what you'll do, here it will be anti-clock, clear. So magnetic field of lines will be going like this, and here it will be clockwise, clear. So what it does, it opposes the change. So a south north pole was coming. In order to push it off, what you have to do, you have to bring a north south. So the current will come accordingly. Clear, everyone? Got it? Didn't get? You can use right hand thumb rule also to see the current direction. One more example I'm giving, I think so you'll understand from this. See, let's say your magnet is coming like this. This is the north, this is the south. Okay. And here your coil is there. Okay. So since this is the north pole, so what is happening? The field lines are going like this. Now what is it has to do? In order to reflect this magnet, in order to deflect the magnet, in order to push it, what it has to do? It has to create a north pole on the outside. So what it will do? How do we create a north pole? By anti-clockwise. Correct. By making a current anti-clockwise. So then it will make the current pass in this direction. Clear, everyone? So this is our north pole anti-clock, and this is our south pole clockwise. Clear, students? Yes or no? So here what it does, high new moon, you're there. It generates a north pole to deflect the magnet. Clear? Anyone doubt? Again explain the charge formula. So charge is nothing but current into dt. I remove the minus sign because charge we can take, if it is negative, it is a negative charge. If it is positive, it is a positive charge. So I is equal to what? What is the current formula? I is equal to q by t, charge by time. So for a small current, di is equal to what? dq by dt. So q by dt. Done. Clear? Anybody doubt? No doubt? Now tell me a very simple question. This is a coil. Okay. And this is a magnet. So magnet is north south. Magnet is moving faster with v2 speed. Coil is moving what? With v1 speed. But I can say v2 is greater than v1. So now what will be the direction coming up here? Do tell me fast. I'll put one more question. Let's see. Try everybody, all three. I need the answer. I think anti-clockwise. If anti it is there, say North Pole. If it is clock, say South Pole. Where is Karthik? Is not writing any answer. Harsh, don't know. No issues, no issues, no issues. See, just understand, bro. If it is going away, it wants to hold it back. So it will create opposite pole. And if it is going increasing, it will try to deflect it. Chalo. Let me explain you. Now, understand, see. So check everybody, always check relative motion. Always check relative motion. Always check relative motion. So this one is going faster, this one is going slower. So what I'll do, I'll stop this, I'll stop this, I'll stop this. Okay. I'll make it zero, speed, make it zero. So what will happen? This one will go with a speed v2 minus v1. Correct? Clear? So now only this is moving, this is stopped. This is stopped. So only this is moving, then this is going away from it. This is going away from it. Clear? So what it will do? Since it is going away from it, so what it will do? It wants to bring the north pole towards it. So what it will do? It will create a south pole. It will create a south pole here. Why? Because it was going away from me. For what I want it to be back. How well it will be back? By attracting the north. By attracting the north. So the first one who wrote clockwise is correct. Lucky bro, not bad. Clockwise correct. Got it? What is it, Harsh? Did you get it, bro? See, north pole first do relative motion. Physics basics. Sir, I made the velocity of this wire 0. I applied that V2 minus V2, V1 velocity that side. Clear? Now, only my magnet is moving and that too away from me. So I want to hold it. How do I hold? Bring a opposite pole so it will attract. Clear? Clear, yes or no? Chalo. Next. Next बच्चों बताओ now बताओ Harsh. Tell me the next now. Tell me now fast kids. Second one is south. How south, bro? See, both are coming towards each other. Both are coming towards each other. Correct. Correct. So I want it to go back. So what I'll do, I'll bring a north pole, no, bro. I'll bring a north pole, no. So that it is pushed back. Now coming to relative velocity speed. So what I do when I make this one velocity 0, I apply the same velocity here but in opposite direction. So only this will be added more. So let's say it is going with V1, this is going with V2. So once you stop, it will be going with V1 plus V2. Imagine two cars, bro. One car is like this, coming like this, and the other car is like this, going like this. If you stop one of them, what will happen? If this was going by 10, this was going by 10. If you just imagine and stop this one, you'll see that this one is going by the speed of 20. Correct? Any person who is sitting here will see that the other car is coming with a speed of 20. Why? Because 10 he only is going. Clear? Like if you have traveled in railways, when you see two trains crossing each other, what happens? If they are crossing each other, like one is going this side, other is going this side, what it seems, they're going super fast. Why? Because double the speed. If let's say this was going by 60, this was going by 60, now since I'm sitting here, so I'm thinking that this is not going, so this is going by speed of what, 120. So this was coming near, north pole was coming near to me. How do I send it back? By creating a north. Clear, Yash? Clear, Harsh? Sorry, clear, Harsh? Now this time it is going away from me. This time it is going away from me. I have to bring it towards the north. So what I'll do, I'll bring a south pole here. Clear? Where is Karthik? He said, do you want to do class? Huh? Clear, everyone? Got it? Clear? Chalo. Now understand, everybody. कह दो सर से, क्या कह दे बताओ. No. I'm in 5 minutes. I am 5 minutes back. चलो, कोई बात नहीं, चलो. जाता है. So let's see students, see a Lenz law and conservation of energy. It's very simple, nothing is there in this. Okay, so when you are bringing this magnet, okay, towards the coil, what is happening? It is creating a north pole here, so work is done in repelling it, so work done again here. Now when you are taking it away, so what will happen? Again they want it back because the flux will be changed, so again work will be done against force of attraction. So no movement, no work, so it obeys what? Conservation of energy. Okay, done, that's it, nothing is here in this. Just go through once, tell me if you have any doubt. देखो बच्चों, simple सा concept है. What is the concept? That when we are bringing the magnet towards this coil, what is happening? One north pole is there. In order to stop it, it is bringing a north pole. So work is done against the force of repulsion because you are bringing it. And when you are taking it away, now it is telling don't go back. So it is creating a south pole that time. And it is trying to hold you back because it doesn't want to change. So there we are doing a work against attraction. So in both the cases, whenever there is a movement, we have to, work will be done. No movement, no work. Clear everyone? Harsh, got it bro? Got it bro, Harsh? Do tell me fast, fast, fast. I just got call from home. So do tell me fast. Got it, everybody? Yes, sir, has got. What about others? Got it? No. Chalo. Now we'll talk about electromotive force. We'll talk about electromotive force, and this what we'll talk about is when you're putting a what is a wire inside a magnetic field and you're moving it, you're making it move, then one force will come. Okay, what is the value of that force and everything we'll talk about. Let's see. Chalo. Done till here. Next, write down electromotive force. Now, electromotive force also very simple concept. Okay, nothing much difficulties here. Now, direction everybody got. How to find the direction? You can use Fleming's right hand rule. In order to, before this, just in order to find, you can use Fleming's right hand rule. Okay, to find it out. Clear? Anybody who remembers Fleming's right hand rule? Come on, anybody who remembers Fleming's right hand rule? Nobody remembers? So if you stretch the first three fingers of your right hand in such a way they are mutually perpendicular, so then what will happen? The first finger will points towards the magnetic field, middle finger points to the direction of current, and thumb will point to the motion. Okay. Chalo. No, yes, no, kids do say it. Anything? Now let's talk about motional EMF. So what you have done, you have taken a magnetic field is there all side, and you have taken a rod like this, and you are moving with a velocity v. Clear? So there is a uniform magnetic field, okay, and you have taken a rod and you're moving with the what is your value v. So in that case, what is the induced EMF formula? What is the induced EMF? Because you are doing a movement, okay. So whenever there is a movement, flux will change, because see, this this wire it is moving no either this side or this side. So the moment it is going this side, the number of flux which was here, now it is changed. So whenever there is a change in flux, what will happen? EMF will come, EMF will come, then current will come. Clear? Clear everyone? Clear everyone? So here the EMF induced is anybody EMF induced formula? Nobody will EMF induced formula? BLV? Nobody remembers? So the EMF induced is E is equal to minus of BLV. Okay. Now, once we got the EMF induced, okay, if I want to find the power required to move the rod, so power is equal to what? Force into velocity. So how will we find it out? Force. How can we find the force? Anybody? What will be the force value? If I want to find the force, how will we find our power equal to force into? Force is equal to what? IBL. Force is equal to what? Okay, we'll come to this. We'll come to this. Otherwise, you won't understand. Okay. This much I think so everybody got it. Okay. Now let's say there is a different setup. Magnetic field is there. And this time a circular, what is say, a rod is there like this, and it is fixed here. It is fixed from here, and it is rotating. A rod is of L length, and it is rotating with omega, So in that case, the EMF induced will be equal to what? half B omega L square. Clear? Can you remember this much? The EMF induced will be half B omega L square. Clear everyone? Clear everyone? Clear everyone? Now. So everybody, we got induced EMF E is equal to minus BLV. What about current? What about current? I is equal to E by R. So that is equal to what? BLV by R. Clear? Clear everyone? So we got the current. So due to the magnetic field, there will be a force. So if force is there, so force formula is equal to what? F is equal to IBL, and that is equal to what? If I put the value BLV by R into B into L, so what you will get? B square L square V by R. This is the force formula. Now the power formula which I wanted you to write earlier, just let me cut this one. Now the power formula, power, okay, the power required to move rod, power is equal to, formula is what? Power is equal to force into velocity. Force I already know, that is equal to B square L square V by R into V. So what you'll get? B square L square V square by R. Clear everyone? See here, clear everyone? Any doubt? Do tell me if anybody has any doubt. Hi Kushal, how are you bro? Chalo, everybody got it till here? Clear? Chalo, no doubt, no doubt. Hi. Chalo. Next, just the recap of the formulas. What were formulas we learned? Okay. Now in this, if sometimes they'll give you frequency. So what we'll do, half B, frequency formula is what? 2 pi f into L square. Clear? So 2 will be cancelled. Clear? Now pi L square will be what? Area. Area of anything is what? Pi L square. Okay. So what you'll get? BA into frequency. Clear everyone? Clear everyone? So if somebody wants in terms of frequency, they give you the frequency of this, what you say, wood or rod, whichever is rotating, then also you can do it. Clear everyone? Chalo. So what are the basic formulas we learned? Induced EMF. Just recap it. Induced EMF is equal to what? E is equal to minus d phi by dt. Clear? Induced current. Induced current. I is equal to minus d phi r dt. Just divided by r. Charge. Induced charge. Or we can say charge due to induced EMF. Charge due to induced EMF. dq is equal to what, student? Minus dq by r. Clear? Just multiplied with dt. Okay. And then we learned about power. That is equal to, power is equal to b square L square V by r. Oh, sorry, V square by r. Correct? Clear? So these all things we learned, student. Any doubt? Anybody? Hi Fad. Now one more thing. If the induced current is produced in a coil which is rotating in a uniform magnetic field. So if you remember, What are the formulas? I is equal to NBA sine omega t. If you all remember, let's write it down. Maybe it can jog your memory a bit. Correct. So if we talk about if induced current is produced in a coil rotated in uniform magnetic field. So in that case, I, if you remember the formula, NBA sine omega t into omega by r, correct? And if you want to find the peak value, so peak value I naught equal to what? NBA, the constant term you take it, NBA omega by r. Clear? Because what is the I formula? Instantaneous current is what? I is equal to I naught sine omega t. I naught sine omega t. So leaving this sine omega t, whatever it is, it becomes I naught. So what was left? NBA by R into omega. This all became I naught. Clear everyone? Clear everyone? Now what all these means? Where n equal to what? N equal to what? Number of turns. B is magnetic field. Omega is angular velocity. And A is area of cross section. We all know. Area of CS. Clear? Chalo, let's talk about our buddy eddy current. Clear till here? Anybody any doubt? Anybody any doubt? Come on, kids. If you want, go through. We are almost done with this. A bit is left. Eddy currents, and same thing for Foucault currents. Also, we call it as self-inductant mutual. That's it. Two is there. Nothing left. Come on. Who else is there? Any doubt, kids? We'll start with eddy current. We'll finish it off fast. Okay. Chalo. Eddy current, also known as Foucault's current. Harsh, no doubt. Good, bro. So Foucault current, it is known after the scientist Foucault. Okay. Now they're known as eddy current because of the pattern, that swirling pattern which comes, like it is like the pattern, that eddish pattern in, what do you say, in that countries they say. Okay. So let's see what is it now. So basically, what is this eddy current? So eddy current is nothing but a current induced in bulk pieces of, some spellings I'm going wrong, pieces of conductors when magnetic flux linked with it changes. So what is telling? Now you have big pieces of conductors. The moment the flux linked to it changes, what happens? Eddy current will come in that. Okay. So we know I is equal to what? Induced EMF by resistance. That is equal to E by R. So according to Faraday's law, E is equal to what? Minus d phi B by dt. So then I is equal to what? We already did, minus d phi by dt by r. Clear? And direction of, we get it from Lenz law or right hand thumb rule. Right hand rule. Clear? Chalo. Now what happens in eddy current? This flow pattern, okay, it resembles swirling eddies. What does this swirling eddies look like? Like these kinds of thing. Okay, clear? So that's why, and it was named after the, I think so, British scientist Foucault. Maybe some can be other also, don't remember. So also called as Foucault current. Clear? Clear everybody? Clear everyone? Now where it is produced, production, it is produced basically in iron cores. Okay, so produced in iron cores of rotating armatures of electric motor and dynamos. Clear? Also you can see in transformer core when we have read moving charges. Clear? Whenever it is experiencing a what? Changing flux, it is there. What are the disadvantage? So unnecessary heating. Next, power wastage. How can you minimize it? By lamination of metal plates. Connect the contact. Remove the contact between the metal plates. So laminate them, lamination of metal plates. Clear? Or you can make some gaps in metal plates, put a slit. Okay. Where we apply application, does it have any use? Yes, it has uses. Application number 1, electromagnetic damping. Electromagnetic damping. Next, magnetic brakes in train. Magnetic brakes in trains. Clear? Induction furnace you can use. Clear everyone? Anybody doubt? Anyone doubt? Now last part, self and mutual inductance. Done. 15 minutes more, we'll be finishing it. Self and mutual inductance. Clear? Clear everyone? All done, all slept. Who is up? Only Harsh. Who all is up? Nobody. Chalo, koi baat nahi, we'll finish it off. Now let's see inductance. Anybody has any doubt? Do tell me fast, otherwise we'll move. Okay. Now we know everybody that flux linked with a coil is directly proportional that flux linked to a coil is directly proportional to current. So what they're trying to say, phi B is directly proportional to current, more flux. Okay. Now, if the coil geometry doesn't vary with time, so what you can say, if I differentiate both d phi B by dt, so will it be directly proportional to di by dt? I differentiate it with respect to time. Now, this is for one turn. What if we have a n turns? So n phi B will be also directly proportional to current. Correct. Now, when we remove this proportionality, we bring a constant that is known as inductance. And that is basically ratio of flux to current. So, the constant of proportionality is called inductance. So it is also ratio of flux to current. Clear? Chalo. Now dependence depends, what it depends, inductance depends, number one, geometry of coil. And number two, intrinsic material properties. Clear? Sure. Now self-inductance. So students, what do you mean by self-inductance? So property by virtue of which the coil opposes any change in the strength of the current flowing through it by inducing an EMF itself. Means, see what happens. A person came, he is telling some slangs. What do? You tell your mind that though is very high looking, what is a very tall, build up, whatever it is, but since it is giving me a slang, I'll go and fight. So what you did, you made your mind and you went for fight. So same thing, whenever a coil is seeing that the current inside is changing, what it does, it induces its own EMF to bring its own current. So this is also called as a back EMF. The induced EMF is a back EMF. Okay. So the current, when it is switched on, it opposes the growth, and when it decays, it opposes the decay also. So that's why it's also called inertia of electricity. Means if you start increasing the current, it will also start its current. If you start decreasing, it starts decreasing itself also. Okay. Means if you say two slangs, it will say two slangs. If you say one only, it will say one only. So it's like the inertia. How much you say, it will reflect on that. Clear, everyone? Clear? Do you want me to write it down, this one, or you got the concept? Just writing fast. The coil opposes change of current flowing through it by inducing. I got it. That's why I'm writing a EMF in itself. Read it once, it will be clear. See what happened, bro. Whenever a coil is there and suddenly the current in the coil changed, so what it will do? It has to, the current suddenly change. It is not able to bear it. What it do? It will create its own EMF and a opposite current. Clear? Clear? it creates its own EMF so that it can counter that previous current. Now, this induced EMF is known as back EMF. This induced EMF is called back EMF. Clear? It opposes both growth and decay of current. So called the inertia of electricity. Very important. See, what they're trying to say is basically same thing. See, what happened is when two people are strangers, when they try to meet you, try to take something from him or ask something, he's like very hesitant. He doesn't want to give because he doesn't know you. The moment you build up a friendship, so starting when the current came and it was building inside, it built up its own EMF to counter that current. Now when the current is about to go, it is really not to go because I'm used to that. So when it is about to go, it has to remove its own back EMF so that it can adjust to the change. It always wants a neutral balance. So when you increase the current, it increases its EMF to increase its current. When you decrease it, it has to decrease its part. Clear? Clear, Harsh? Or you didn't get it? Say it fast. Now, what are the formulas in this? We know if you have taken a coil with N turns, one second. Chalo, let's see. Next. So coil is there, N turns is there, current is there, I. 1 second, kid. Chapter wise. Only you and me are there, no? Chalo. No, let's see. So we have a coil, N turns it has, current is I. This much we know. Now what you can say? Total flux phi will be equal to what? N into phi b. For 1 it is phi b, and for n it is n phi b. And this whole thing is directly proportional to current. So if I want to remove the proportionality, n phi b is equal to what? Li. Correct? Just now we talked about. Clear? So L is the constant called the coefficient of self-inductance. So from here we can get the value of L. L is equal to what? N phi b by I. Clear any doubt? Check it. Clear any doubt? Check it fast. Check it fast. Now, if n is equal to 1, we can say if n is equal to 1, we can say phi is equal to Li, also same thing. Now, E is equal to minus of d phi by dt, and that is also equal to di by dt. L times of di by dt, if you remember. E is equal to what? D phi by dt. So minus L di by dt. L is constant. Clear? Now, if n coils are there, so this much we got done. What is the unit? Henry. Clear? Now, sometimes they very rarely, but they do series and parallel. If series you are connecting of L1 and L2, two are there. So in case of series, it will be L equal to L1 plus L2. Or in case of parallel, 1 by L is equal to 1 by L1 plus 1 by L2. Clear? Same thing, just like resistor, nothing. Huh? What is the formula of L in terms of mu naught and all that? Mu naught n square A by L. Clear? Or mu naught n square AI. Clear? Now we all remember energy stored in an inductor half Li square. Energy stored in an inductor, just formulas I'm putting up. In an inductor equal to half Li square. Clear? This is all about self-inductance. What about mutual? Clear this? Now next, mutual. Now mutual inductance, two coils are there. One is like here, another is here. Flux linking will be happening. So flux here for mutual will be phi is equal to Mi. EMF E is equal to minus of M into di by dt. For mutual, the what is it? This one instead of L, it will be M. Clear? Now, one more formula for mutual inductance, very important. Okay. Whatever the first coil is inducing in the second also will induce in the first. Clear? So M21 is equal to M12, and that is equal to M, and that value is nothing but mu naught N1 N2 into AL. Clear? Or what we can say, that is equal to mu naught. If you want to write in terms of capital N, this is small n. So capital small n is equal to what? Capital N1 by L. It is number of turns per unit length. N2 by L into pi R1 square into L. So one L got cancelled. So what you will get? Mu naught N1 N2 pi R1 square by L. Clear? Clear? No. So this M also, just like L we talked about, M depends on what? Geometry of coil. Geometry of coil. Number 2, distance between two coils. Distance between two coils. And number 3, relative placement or basically orientation. Clear? Clear? So it's almost me and you all done. Now, if you have self-inductance of a long solenoid, just formula I'll put up. Self-inductance of long solenoid. So first, total flux equal to flux through each into total number of turns. So what you'll get? N phi is equal to mu naught NIA by L into N. Clear? Now, one more formula. L in this case, L for the long solenoid will be mu naught N square A by L. Now, one question keeps coming again and again. What is that question? That what if some other core is placed? If other core is placed, means inside you have put up something else. Okay. So then in place of mu, it will be nothing but mu naught into mu r, relative. So now L value is nothing but mu naught mu r N square A by L. That's it. Clear? Clear? Now last part, AC. AC, I'll just give you the formulas, okay? AC generator, okay? In case of AC generator, what are the important first principle? So works on EMI, electromagnetic induction, works on electromagnetic induction, magnetic induction. Clear? Chalo. Next, what are the workings? So phi flux is equal to what? BA cos omega t. This is for one turn. For n turns, phi is equal to what? N into B dot A. So I can say NBA cos omega t. Clear? Where theta angle is equal to omega t. Clear? E is equal to what? Minus d phi by dt. For n turns, minus d by dt of NBA cos omega t. So what will happen? NBA is common, it's constant. So d by dt of cos omega t. So what you'll get, NBA, cos is what, sine, minus sine, so sine omega t, that minus will be gone. Clear? We got the flux. Clear, everyone? Now, if we compare E naught value, E is equal to E naught sine omega t, E naught will be what? The peak value NBA omega. Clear? And omega is equal to what? 2 pi f in terms of frequency. So E is equal to E naught sine 2 pi into frequency, or f into t. Clear? For AC, like normal house, the frequency is what? 50 hertz. Frequency what we have is 50 hertz. Clear? Done. Any doubt, bro? This chapter is done. Took a lot of time. That sums up the ends of the chapter. 133 minutes. Not bad, not bad. Nobody asked any question. I was just keeping saying. So, okay, keep it till here. Clear, Mr. Harsh? Bye bye. Chalo.